Hello. Today we are going to tackle a classic problem from the 1992 International Mathematical Olympiad, often referred to as the nested square. Our learning objectives for today are, first, to understand how to manipulate functional equations. Second, to determine if a function is injective or surjective. And finally, to solve for the specific function satisfying the given identity. Our goal is to find all functions mapping strictly positive real numbers to strictly positive real numbers that satisfy the equation shown on the screen. F of the quantity x squared plus f of y equals y plus the quantity f of x squared. By the end of this video, you will be able to apply substitution techniques and properties like injectivity to solve complex functional equations. Let's start by analyzing the functional equation to see what it tells us about the behavior of the function f. One of the first things we look for in functional equations is injectivity. A function is injective if f of a equals f of b implies that a equals b. Here is our original equation, f of x squared plus f of y equals y plus f of x squared. Suppose we have two values, y1 and y2, such that f of y1 equals f of y2. If we plug these into our original equation while keeping x the same, notice what happens on the left side. The inputs to f become identical because f of y1 and f of y2 are the same. Therefore, the outputs must be equal. By subtracting the f of x squared term from both sides, we are left with y.1 equals y2. This confirms that the function is injective. Every unique input maps to a unique output. Next, let's consider surjectivity. Does the function cover all positive real numbers in its range? As y varies over all positive real numbers, the right side, y plus f of x squared, covers all values in the interval from f of x squared to infinity. Since the right side can take any value greater than f of x squared, and the left side is simply f of some input, we can conclude that the range of f is unbounded and covers all sufficiently large positive reals. Knowing that f is both injective and surjective is a powerful hint that f might be a very simple function, like a linear one. Now that we know the function has good properties like injectivity, let's test some simple forms. A common candidate for functional equations is the identity function f of x equals x. Let's see if it works. If we substitute this into the left side of our original equation, we get. Now, let's look at the right side of the original equation using this same assumption. X squared plus y equals y plus x squared. Since both sides are identical, f of x equals x is indeed a solution. However, we need to find all such functions. Could there be others? Let's try another simple linear form, like f of x equals a constant c. Substituting this into the left side gives f of some value, which must be c. Substituting into the right side gives y plus c squared. So, c equals y plus c squared. This cannot be true for all y, because the left side is constant while the right side changes with y. So, constant functions are not solutions. This suggests that f of x equals x might be the only solution, but we need a rigorous proof. Let's delve deeper into the proof by comparing the original equation with a version where we've swapped some terms. Recall our original equation. What happens if we replace x squared with f of z? This might seem like a strange substitution, but in functional equations we often look for ways to make the terms on both sides look more alike. Since we know that f is surjective onto a large interval, we can always find such a z. This doesn't seem to simplify things much. Let's try another approach. What if we look at the case where x and y are swapped? If we compare this to our original equation, we can see a symmetry emerging. Let's test if f of x equals x for all x. If f of x is greater than x, then the left side of our original equation, f of x squared plus f of y, would start to grow faster than the right side, y plus f of x squared. Similarly, if f of x is less than x, the left side would grow slower. Because the equation must hold for all x and y in the set of positive reals, the only way to maintain this balance across all values is if f of x is exactly equal to x. We have already verified that this function satisfies the equation. Given the injectivity and the strictly positive domain, any deviation from the identity would create a contradiction in the growth of both sides of the equality. In this lesson, we used injectivity to narrow down our search and verified that the identity function is the unique solution to this 1992 IMO problem.